Good morning, ladies and gentlemen. It's an honor and privilege to be here this morning with your presence in this webinar, a 2 hours webinar organized by PDH. I see on my screen a few chats from Randall, Matthew, and Mark, and yeah. Okay. As you know, if you have any question, you can post it on the chat box, and they will be responded by the administrator. Okay, so today's webinar, which will be 2 hours, the topic is causes of structural failures and forensic engineering process. The cover image is one of the cases that I was the designated expert structural engineer in this litigation matter. It's this case was based on an incident that occurred at LAX, Los Angeles International Airport. This image, I did take this image myself when I was doing this investigation. The airline logo and everything is stripped out of this image. We removed it by photoshopping it, but exactly this is the location of the incident. This is very similar to the aircraft that occurred. This incident occurred, and this on the right-hand side is the jet bridge. It's not exactly the jet bridge that failed, but it's from the same manufacturer, the same model, everything. So I was at the LAX about 2 years later or a year later, and I had to investigate. Anyways, we will go through this case through this slide. We have about 71 slides, and it will be one of the cases that we review today. All right. So during the presentation, if you have any question, I welcome you to raise your hand by the icon which is there in the chat box, and Igor is asking a question. Do you see me? Of course I see you. I see you now, and hopefully you can see us. Okay, so just you have some kind of idea who is providing you this presentation today. I'm a licensed structural and civil engineer. I primarily practice in California. I live in Southern California, and but I do practice in other states as well, and Canada. I have active projects and litigation matters in Canada and several other states. So my work is primarily, I've been practicing nearly 40 years. I've worked primarily as a forensic structural engineer. Sample of some of my work, I've been designated by US government and some law firms and insurance entities for various litigation matters as an expert structural engineer. As you can see here, just very briefly, done hundreds or maybe thousands of projects throughout the United States and North America. I've been principal engineer for project for NASA and other entities. I was the director of CEOS, which is a Structural Association of the Structural Engineering Association of Southern California. And I've been interviewed by news agencies and so forth, and History Channel, and so forth. Anyway, So just some kind of brief idea that who I am, and so what's my qualification when I'm discussing these topics. So the course outline, as you had noticed in the brochure, would be 6 parts. So we'll go through each of these parts in extent, and we'll discuss each of these. By the way, our organization stated that there are about 70 attendees today in this presentation from throughout, from different areas of United States. So just to have some kind of idea about our audience. All right, so the first section would be well, that was the first 6 part that it was on the first section, and then there are more parts, a total of 11 sections in our course outline. So the first section, we're going to discuss structural engineering design errors, and I make sure that I time myself accordingly, so there won't be any material left at the end of the presentation, at the end of the 2 hours by 1 p.m. my time in California. So addressing subtle structural issues, failing to understand project objectives, underestimating demand requirements, insufficient design verification, and failure to validate the design assumptions. So we're going to touch on each of these briefly and get some kind of idea about these. My understanding, based on my past 15 years of been providing webinars and presentation to engineers, is that the audience usually have a wide spectrum in terms of their background, qualification, and experience. Some of them are new, 2 years fresh from university, some of them 50 years from graduation, some of them engineers, some architects, some general contractors, some mechanical engineer, wide spectrum. So I try to make sure that the webinar is interest everybody as much as possible, because I can't focus only on one group, like just the structural engineers, or I know majority of the audience is a structural engineer, but there are some other from some other professions. So, and also the other factor is the experience, the number of years involved, and also the area of expertise of the audience. So in order to satisfy these in the most efficient way, that's my effort is. So forgive me if a little bit sometimes appear boring to you, or sometimes appear a little bit, you know already the information that got discussed. Just bear with me. We move on quickly and we go to the other area. So addressing subtle structural issues. Most of us, when we accept an instructional assignment, we are primarily focusing on strengths issues. Okay, my building doesn't collapse, I'm good. That's obviously the most important part. But there are other important factors as well that do not involve life safety. For example, I give you a few examples. But because these are court cases, some of them are still in litigation. I can't provide too much information, but I provide information sufficient for us. So For example, I had a case a few years ago in Alabama. It was one of the largest manufacturing automobile in the world, and their manufacturing facility in Alabama, they had robotic system that was in that facility that was installing various components to each vehicle. And they hired a structural engineering firm that was going to install a 30-foot by 30-foot by 30-foot system, a structural system above the production line. So whenever these cars went through, the robotic arm came in and functioned and installed the components. So what was wrong with that product, that structural moment frame that was there? It had too much displacement. Why? Because the robots had to move, stop and go motion, and every time they did that, as soon as they stopped, because they're shaking on the moment frame system, and the moment frame system was not rigid, sufficiently rigid, and then it induced a significant amount of displacement, which was beyond the tolerance of those sensitive robots. The robots, in their specification, they had maximum 1.5 millimeter allowable displacement in order to function properly. As soon as the displacement went above that, the whole thing shut down and the manufacturing facility stopped working. So the deflection was way beyond displacement, was way beyond that. It was in the magnitude of like maybe 6 inches. And that's what I remember. In some cases, 6 inches, but when the force was high, and other cases was about 2 inches, 3 inches. But again, as you know, 1.5 millimeter is a fraction of an inch, probably about 1/20th of an inch, and that was not acceptable. That's one subtle structural issue. The designer somehow did not take that into consideration. It was not a structural engineering firm. It was a civil engineering firm that practiced the structural. Another case here in LA, we have a 5-story wood frame building on the top of concrete podium. Very expensive condominiums, average price $3-4 million, all from foreign countries, bought that from Hong Kong and different kind of countries, bought these beautiful condominiums. And then what happened is the concrete podium, the concrete two-way slab with concrete column caps, it had significant amount of deflection, way more than what is acceptable by the building code. And how much? About 3 inches at the concrete podium. And for some reason, on the very top floor, it was again an additional deflection because of some wood frame issue there. So if you went on the very top floor and you did a manometer survey, checking the floor elevations, it was almost 6 inches from the entrance to the end of the condominium. And you can imagine what kind of concern would create for this HOA. So anyways, it was a $30 million lawsuit. And again, the building is structurally sound, no safety concern. But again, the long-term deflection, as we know, is a different kind of concept with concrete. We don't have that issue with wood or steel or masonry or glass or fiberglass or aluminum, but we do have that with concrete. Based on my experience, the immediate deflection that we calculate, we need to double that in order to account for the 5-year long-term deflection because of the creep and other issues with concrete. And when you do that, you have to be very careful, either have high chambers, or have bigger slab, or have there are different ways, as some of you might know, put negative reinforcing, top reinforcing right under the concentrated loads. That would reduce, believe it or not, it will help controlling the deflection, or post tension straps, putting in addition to the mild reinforcing. Anyways, understanding the project objective, the same concept that I just explained a few moments ago. Essentially, we need to like both incident cases that I indicated a few moments ago. The project objective is as indicating what the requirements are. Understanding the demand requirement, number 3. Demand, whether it's a loading demand, deformation demand, or any kind of concept that would impact and dictate us the way we design our structural system. Insufficient design verification. Let me see how I can give you some example. Design verification. We had a case recently in Las Vegas. I was a structural engineer expert on that. And let me give you an example. I think you might be interested in that. This was a large development. Again, high-end residential, $2 million each property, single-family homes, Las Vegas area, and maybe about 100 development. And then this, again, civil engineering company that did the practicing structural, they did the retaining wall, site retaining walls. And these site retaining walls were long and they were tall. And unfortunately, after a year or so, they failed. How they failed? You could see big cracks in these tall retaining walls. You could see through the CMU wall. You could see the other side on the top area that because it was projecting a few feet above the soil. And the sensitivity of this, the design verifications I'm trying to explain here is that these retaining walls were supporting the backyard of these homes. So what happened is when the homeowners wanted to construct a swimming pool, or they wanted to do an improvement on the backyard, it would directly impact the loading condition on these retaining walls. And that was not accounted for. There was a small little disclaimer somewhere that says, this is our design criteria, the loading condition. But again, there were other issues as well. Not only that, they did not account for any kind of improvement, and essentially the walls failed, and that's just one of the subtle issues. And so validation of design assumption, the same. So let's move on to the next next part, defective construction. So again, just keep an eye on that spectrum of the audience. Some of you might know some of these topics. Some of you might be interested to get more information. I just try to make it interesting in terms of learning objective for all of us. So there are two types of defects, as you know, in construction: latent versus patent. Patent defects are the ones that are obvious. You can see them. And it's generally during a visual inspection by normally an ordinary person, doesn't need to be a highly skilled structural engineer. It can be observed. like you see cracked beam, you see cracked walls, you see cracked concrete floor, cracked foundation. These are obvious, right? However, there are other types of defects, which we call them latent, which is referring to the defects that are not visually observable. Usually you need a professional, licensed professional to observe them. For example, let's say excessive deflection in a concrete parking structure or parking podium or a podium slab. You need specific instrumentation. You need manometer instruments in order to determine, okay, what is the deflection and what's the allowable, how does it relate to the maximum limit, and is it excessive, it's not excessive, how is it impacting the structure, and so forth. Okay, so that's one of the concept that is important in our practice. Then the five items that we are looking at here, I'm sure all of us, most of us at least, have dealt with these items in the past. Undocumented foreign material that sometimes occurs, and it surprises the structural engineer, designer involving in a case in a project. Examples of these are bolts. You know, we have A325, we have all different kinds of bolts, and each of them have different specification, different parameters, and ASTM and so forth. And we recently had a case that structure, steel structure, larger steel structure, just one story though, it failed during the construction. What happened was few workers got injured, one of them seriously injured, in coma for several months, but there were so many issues in this project. Number one was improper temporary bracing during the construction. But another issue which relates to undocumented foreign material was we found some A307 bolts, erection bolts, and I don't know exactly what they were for. We were guessing that they're for erection purposes, but we found them. And A307, as you know, and then we looked at what was some kind of identification on the back of the bolt, and we found these are the B types, which are the inferior quality, and so forth. So, and we don't know where they are manufactured and so forth. So that's an example. But again, there are, the mill certifications that we ask for steel sections. That's another reason for these undocumented foreign material, because God knows where these are made and they shipped here to US or to our ports and so forth. Erection and fabrication issues. Yeah, I was just talking about this failure that occurred. It was a erection issue. The erection related to temporary support. The temporary support, lateral temporary support by lateral braces that they had with these cables. And in order to resist the lateral movement during the construction, you might be aware when there's the construction going on with the steel structure during the erection, the structure has to resist certain lateral load. That's by building standards. It tells you exactly how much those forces are. I know you put the wind load, you put the seismic load during the construction, which are very minimal, but then there are construction loads that you have to put. So yeah, then we see what's the worst case scenario, and we determine we go from there. However, the bracing for this particular case that I was talking to you was not the diagonals. They were supposed to go get anchored into the concrete below. They did not. They were attached to K-rails. What's K-rail? K-rail is like a 5,000 pound concrete piece. Usually government transportation entities use that. Here in California, Caltrans use that. So there's a block, 5,000 pound concrete. They bring it to the prop site, and then they connected these to these blocks, and they relied on friction because the horizontal, and then we calculated the demand was probably 3 times more than the capacity, the resistance of this, and they just failed during this issue. But anyways, I had another case a few years ago for a hospital, similar case, the same thing happened. Construction sequence, that again is related to the construction, nothing to do with us as the structural engineers, but the sequence sometimes can make a big difference in results. Whether I'm sure you know about the examples of that. Let me give you an example that's easy for all of us to understand. For example, let's say for a concrete slab, elevated concrete slab, and the next phase is to go above and do the next concrete slab above that. There's a period that you need to shore this concrete slab below before you can put load on the top, or there's a period before you can remove the shoring from the under the slab. So these and then when you're dealing with high rise, the sequence becomes so critical because the time and everything meeting deadline, and then that construction sequence sometimes can cause problems, and the problems unfortunately result in a dispute and so forth. That's just one example. Other examples, for example, when you're underpinning a building, again, you go A, B, C sequences. When you're underpinning, you don't dig under the entire footing, you just go sequences and so forth. And then that sequencing is something that we as a structural engineer have to take into account. Of course, the contractor has the he can choose the method and means the way he wants to construct the system. But again, we need to be aware of that. For workmanship, you're all familiar with that. That unfortunately impacts us as structural engineering, brings us into the dispute as well sometimes. And effective temporary support. That was what I was talking about the first case, that temporary support. The temporary support, you need to be very careful with that because they have their own standards under International Building Code. There are ASTM standards that are specifically written and published for that purpose, all the loading requirements, everything, and they have to be used. Of course, not all of us get involved in temporary support design. There are some engineers that do that as a specialty, but again, when it comes for our review as a structural engineer of record or EOR engineer of record, is a good idea to look at them. Okay, so material deficiencies. These are the 6 most common construction materials that is used today in United States, in North America. Of course, fiberglass is another item in addition to the glass, but that's a little bit probably less than 1%. So the concrete, there are 6. There can be 6 issues with respect to concrete deficiency: mixed design, improper reinforcing, improper replacement, improper curing, inadequate vibration, and on-site water addition and so forth. So forgive me, I have okay. Roberto. Ah, I thought there was a question. Okay, so concrete mix design. I don't know if any of us have dealt with that issue, but I haven't dealt with it, but I've seen cases that involve this concrete mix, and any kind of dispute, that can be one of the items that we might keep in mind for the record of the mix design. Did it meet the requirement that the structural engineer identified in his specification and journal notes? Did it meet the did it come to like 3,000 psi, 5,000 psi? What was the design? That's important. Sometimes you have to get the record of even the mixer trucks that they bring them in. So, and then there are reinforcing issue, improper reinforcing versus improper placement. These two, the placement, obviously we know sometimes, as you know, if the D distance, whether it's a negative rebar or a positive rebar, if the D distance in a 12-inch slab, if it's changed by 1 or 2 inches, it can make a big difference. So, and I've seen that in some cases when you do GPR, ground penetration radar verification, that the rebar placement is off by like 2 inches of problems, cracking and other things. The improper reinforcing, it can happen when there's a good example. When the rebar size, for example, from a number 8, for example, goes to a number 6 by error or whatever, and it was not caught during the inspection. That can be an example. Proper curing, we're aware of that, you know, in summertime, in wintertime, depending on which zone, geographic zone we are. Summertime, you know, the issues maintaining the moisture content of the concrete until it cures, fully cures. There are requirements for that, keeping them wet and so forth. In wintertime, then other criteria as well need to be very careful. It impacts the curing process. Vibration, that's obviously the honeycomb and things that are as a result of improper vibration when we're dealing with large volumes. And of course, on-site water additions, which we all have that problem with that. Okay. So that is very sneaky. Sometimes there's no record of that, but as you know, it results in heavy deflection issues and displacement. Okay, so the second common construction material, let's see what kind of issues we might have with them. Fabrication erection, improper installation of connection, and weld quality, misalignment, localized failure, lack of environmental protection. Okay, so let's just start from the last one. Galvanizing. Galvanizing, as you know, is one of the methods when we are dealing with the steel to protect them against aggressive environment. For example, here in California or Florida or areas that you're near the ocean, you deal with that a lot, and it's very, very aggressive. It can destroy your building, God forbid me, and you need to be very careful with that. And the galvanizing, if it's not done properly, it's just essentially useless. It has to be done properly with all kinds of details and requirements that has to be done. Another method, if possible, is stainless steel. It can assist us. It's a lot more expensive, welding issues and so forth, but it is done in some cases. You don't want to build a structure with that, but some components of that, like canopies or exposed connections or guards, handrails, these examples you can. Okay, localized failure. Let's jump back to A. From F, let's just jump back to A to keep a smooth flow. Error in fabrication erection. Again, these are construction issues. These are not our issues, but again, they happen and they cause dispute, and they bring structural engineers into the dispute, even though it's structural engineers' responsibility just to review them. I had one case here in Southern California, a hospital, 5-story hospital, that I think is a good example of this issue by fabricator. Very good fabricator, but I think they subcontracted to it was a hospital, and hospitals in California, they don't go under the Department of Building and Safety. They have their own entity in California. It used to be called OSHPAT, Office of Health and State and Health, the rest of that. Now it's called HCI. A few months ago, they changed the name. They're responsible. That organization have significant number of highly qualified structural engineers, highly qualified licensed architects, mechanical engineers, and so forth. Lots of them, God knows, probably over 1,000. And each building has to go through them. It takes probably, if some of you probably are from California, you know that sometimes it goes through 8 cycles of plan check correction, and that can take easily a year. It's very, they scrutinize everything. And because earthquake, during the earthquake or after earthquake, hospital have to remain operable. And so that was one of the hospital. That was hospital. They have their own inspectors. I mean, I take that back. They have a specific inspection requirement that is much more stringent than regular inspections. They have their own inspectors, but for this particular case that we are talking, I'm going to talk about, there were other entities that doing the inspection, private entities that for this particular steel case. So 5-story, they brought all the components to the building, and they erect them. 5-story, inspector came in and checked the weld. The welds, some of them were a little bit off from the specification, the structural engineer. A little bit off, not too much, a little bit off, like about, instead of being half an inch, they were like 7/16, or they were shorter, or they were a little bit. So anyways, to cut this story short, there was a lawsuit. Believe it or not, they have to disassemble the entire building, bring it down to the ground. I was the expert, structural engineer expert on that case. I was hired by the defendant, fabricator, and so forth. Anyway, I need to go a little bit faster because we are on 9th slide, so I apologize for that. It's a little bit too fast. So, improper installation of connections. That hospital case that I said, that was one of the problem was the connection installation that they had, and adequate weld quality. the heating process, the cooling process, all those issues, the thickness of the steel determines how much of preheating is required and cooling is required. Misaligning of the members is when, for example, when we are doing connections, sometimes these members are misaligned and that can cause problems. Localized failure, again, these localized failure are not necessarily as a result of a structural engineer work. It can be resulted from just imagine the Hyatt Regency. The method that means the accumulating force as a result of a change in the load path and localized failure and the global failure. And okay, next material is wood. Inadequate moisture contact, expansion, contraction, lack of environmental protection, lack of proper maintenance, dry rot, insects, fungus, construction error. Just very quickly touch on all of these. Moisture content. Have you ever been to Venice in Italy? Okay, the entire Venice is on wood piles. These wood piles go into the water below, and they've been there for hundreds of years. So does water destroy a wood structural member? It depends. If the moisture content is saturated, above saturated level, very high, almost like very high, then no, it doesn't allow growth of any fungus or any damaging process. It doesn't allow that. However, if it's above like 16% and like below 60 or 50, it can cause problems. It just destroys the wood very quickly. So let's keep that in mind. Expansion contraction, we're familiar with that, especially on roof, and a lot of disputes I've seen because of that. And we have a case study towards the middle of the project. I'll explain to you that, especially on roof, when above is hot or cold or vice versa, below in the attic. Lack of environmental protection, we know about that. For example, not having pressure treated material, wood material when it's used in the exterior application, lack of proper maintenance, maintaining the wood condition, when there's problems, you need to attend it, remove the part that is rotted and repair it with epoxy or whatever it can be, and sand it or do the annual maintenance when they're exposed. Dry rot, insect, fungus, we know about that. Mostly when we have humid environment that can occur. Construction error, the joists have a camber. Wood beam have camber, glulam beam, and sometimes they're specially designed or manufactured based on the structural engineer specification. Sometimes they just come with a little bit of camber. Sometimes I've seen the contractors put them upside down. Instead of camber going up, they go down, and that can cause a problem. And a lot of other construction errors examples. Okay, let's take a look at this. This is one of the cases that I had in Washington State. These rails are new. Before, they were old rails and they failed and caused 2 individuals from the second floor fall and caused them serious injuries. So this is after the fact. The individual was about 300 pounds. He was about 6 foot tall, and was a guest for the homeowner. There were 2 guests from homeowner, and the homeowner bought the house from a flipper, and the flipper installed these handrails without a permit. And I can show you the connection. It's hilarious. And this individual leaned, they were trying to take picture and then he fell, unfortunately. So I was expert construction on this case, and this picture, as I'm not sure if you can see that, here is the connection. This is after the deck was removed, the handrails were removed. These white areas are where the poles, the vertical members were connected to this ledger. And this is the connection, two nails. See the nail, and probably the lever arm is about I don't know 2 inches, and you know nail withdrawal resistance extremely low. You can't rely on, and then in looking at this bottom connection, you know it has to handle the tension and compression that nails, and obviously it failed and it didn't work. So this is after the fact. After the fact, they had to put these bolts and these posts 4x4 force and in between. And of course, this is the proper way of doing it. And another example in wood construction. Again, this is a construction. He didn't have a permit. It's nothing to do with engineers, just the contractor. And here another example of contraction and the wood issues. This is a roof. It's from crawl space. As you can see, these are OSBs. These are the trusses every 24 inches. This area, this line, is a butting joint of 2 pieces of OSB. Okay, there's no spacing between these, and so it doesn't allow for expansion and contraction of the OSB, and therefore it caused bumps or humps on the roof. So when you were standing on the front yard, you could see the humps on the roof all over the place. And you go back to APA requirement, they specifically say that you have to put 1/8 inch gap in order to accommodate that. Anyways, next material is masonry. Inadequate weatherproofing, deficient masonry units, improper mortar, thermal expansion, deficient expansion, and control joint. Okay, some of them are very obvious, but I had to mention them here. Weatherproofing, deficient masonry unit, improper mortar. Again, same discussion that we had for the concrete mix, the same thing here. Thermal expansion and expansion and control joint. Essentially, we are discussing the same thing, more or less, unless you want to also keep in mind about these facades, especially in Eastern United States, New York, and so forth, which freeze and thaw can cause these facades fall off the building, and sometimes they fall 5-6 story building. That is an issue, but thermal expansion, generally speaking, we are talking about longitudinal and usually every 30-40 feet, architects and engineers like to put like vertical expansion or control joints in order to accommodate that. However, sometimes there are exceptions. You don't have to put that, depending on the construction condition. I've heard that sometimes it can be avoided, but most of the time it depends on the construction configuration. Excessive loading. Number 4, depending on the material, the response is different, and depending on the load duration, and depending on whether the material is brittle or ductile. What is load duration? Load duration, in my opinion, is extremely important. Load duration and load condition versus static versus cyclic loading. Static or permanent loading versus cyclic loading. So just to touch on this, load duration, as we all know, in NDS, National Design Specification for wood, we have a load duration factor only for wood. We don't have for any other material. It varies from 0.9 all the way to 1.7, depending on what kind of load, whether it's roof loading, dead load only, or snow load, or seismic load, or wind load, or impact load. We can increase the allowable stress design, allowable stress with that load factor. We can't do that with any other, but we have to be careful. Sometimes when we come in for a roof that is constructed with wood members, we say, okay, they allowed for the 20 pounds per square foot. That live load, construction live load, I'm going to put, now I'm going to put 15 or 20 pounds per square foot, the same amount of load as that was in the design general load sheet of the original structural engineer. I'm going to put more or less the same weight as my solar panel or whatever, roof garden or whatever. I'm going to put that on, not exceeding that. Therefore, if it's a steel construction or roof is by concrete, yeah, maybe it's not a big deal. Although we have to watch for the seismic mass that you're adding on the top, and the threshold is 10% by building code. But forget about that. Let's focus on the gravity, which gravity is only 5% threshold the building code allows. But here, one thing that is apart from that 5 or 10% issue is when you're dealing with wood, the load direction from 1.25, which is roof live and dead load, it immediately drops to 0.9. That's in NDS. When you only have dead load, the load direction factor goes to 0.9. So instead of 125% of allowable stress, you get 35% reduction, and it goes to 9.9, 90% of the allowable stress. So let's say it was 1,000 PSI, instead of 1,250 PSI, it drops to 900 PSI. And I've seen with my own eyes building collapse like that. Specifically, solar panel installation, which they were adding, instead of a screw, they were adding dead weight for the uplift. So that's one thing you want to keep in mind. And then, of course, brittle material, you know about that. Okay. One example, this is here in Southern California beach. You see this beautiful handrail? I was explaining to you about the galvanizing material. This handrail, everything here is a beautiful, very expensive waterfront feature that the government built. And what's wrong with this handrail? The handrail for handicap access, and these are the waves. It's deflected about 3 feet at the top, or 2 feet, something like that. Something, I didn't measure it, but significant amount, maybe 12 inches, maybe 24 inches, something like that. And that's magnitude is showed here. And what happened is, what is shown here, what happened is over the course of like 2, 3, 4 years, the waves constantly hitting this handrail, and it caused displacement so much, and also corrosion. So the galvanizing process apparently wasn't properly done. Anyways, these handrail, this picture is from 4 years ago. When you go there now, they don't exist. They're not there. They're gone, completely gone, and they're in the process of reconstructing. Okay, another example, I was just explaining to you about the wood material. This is another case that solar panels, which are very environmentally friendly. Everybody loves them. I love them. They just have to be done properly, very, very carefully done. And sometimes they don't even put them with the structural engineering involvement, which causes a lot of problems. This one, I think they didn't have a structural engineer. So what happened is, this is an expensive home, and there's nothing. I'm sorry. There's nothing wrong on this side because they're just sitting on the roof. On this side, problem. Let's take a look. They're elevated. They're elevated way above. So this roof slopes towards left. That part from this ridge slopes to toward the right and is going down. And then contractor decided to elevate them like 6-foot vertical poles or vertical posts, and they put them like that. And then you can figure out the problem, concentrated load going into the members, and also the wind uplift and all kind of stuff. So it caused the fracture of this ridge beam. This ridge beam is exactly under here, and they were not accounting for, there were complications on there. So I required immediate temporary shoring, which they put here as on the bottom. You see this fracture is on the top. It's very, very serious. And the fracture comes in here on the bottom as well. These are temporary shoring. That was exposed wood, so you could see, but imagine if it had drywall and ceiling finishes, it would be one of those latent defects instead of being patent. Okay. Deterioration and degradation. Concrete and steel behave differently in this area. With concrete, we have corrosion and we have a spalling. With steel, we have other issues. Corrosion, again, I don't want to bore you. Corrosion in aggressive environments, which, near ocean, as long as you're within 5 miles or 2 miles, 3 miles from ocean, it can be serious. The more close you get, the more serious. So epoxy coated rebars are one of the solutions, and adequate coverage of the concrete, that's another solution. As you know, when rebar in the concrete corrodes, it expands, and it expands several times than the original material, and that force is enormous and causes a spalling, cracking and spalling of the concrete. So be careful whenever you go and you see efflorescence on a concrete material, or you see on a reinforcing a CMU wall, masonry wall, corrosion can happen there. So obviously, it cannot be life-threatening within like first 6 months or a year, but over the course of years, you saw what happened in Florida. It can be very, very, very destructive. Anyway, steel, corrosion, the same issue. Incompatible metals. Some of you know that, but I briefly touch on that. Yeah. If you're constructing whatever it is, a bridge, a structure, a component, handrail, whatever, and you're putting two different metal, steel and aluminum or other, these two, they can have a destructive interaction at the point of connection, and it can destroy both members. So we need to be very careful with that. Keep that in mind whenever we have two different metals connecting together. Fatigue and cyclic loading, that's completely different animal, very serious. And I've seen it many, many times causing failures. And we touch on that in further few slide down, because one of the cases that LAX, that was the problem. Deterioration and degradation, weathering and dry rot fungus. That's very common. I'm sure everybody is aware of that. Sometimes you're forced to remove and replace. Sometimes you can just do the repair, but the repair has to be done properly. Epoxy, there are other methods. Okay. CMU. Weathering issues, freeze and thaw damage that we discussed, corrosion and modal degradation. Similar to concrete that we discussed and similar to the defect that we discussed earlier. So number 6, documenting the failure. So Let's say there's a failure and we are at the site and we want to document the failure. Sometimes we go a year after the incident, but still there are ways to do that. And that's why preserving evidence becomes so crucial. Sometimes you're there immediately at the, a day or 2 day or a week after the incident, and still everything is untouched, which would be under the perfect condition. That would be the best. So identifying valuable physical evidence, whether it's a fire, mudslide, flooding, earthquake, just gravity failure, whatever, or wind, whatever it is, there are evidences that we need to collect. Let me give you a small hint for fire, for example, that it's going to be very helpful for you if you get involved in a fire investigation. This topic, I have other programs on fire and flood and mudslide and earthquake scenarios, but I just touched base on that. And those webinars I discussed this in extensively, but here I just touched on very briefly. You go into a structure and you don't know what kind of temperature it reached during the fire. The only way you can have some kind of idea about that is by looking the surrounding. One of the good example is the glazing. You pull out the glazing specification depending on thickness and so forth, and if the glazing is intact, then essentially telling you that no cracks in glazing, then it tells you, okay, the threshold of the temperature, that's how much it reached. Okay, and then you go through the process and see what kind of material you had, whether you had wood, steel, concrete, and you verify the maximum temperature that they can stay within without any damage. But if you're glazing, on the other hand, if our glazing all cracked, and boy, that tells us that the temperature went in that air environment within that structure, it went way beyond glazing glass tolerance. So that's just a hint for that as a physical evidence. That could be one of them, but there are a number of valuable evidence, physical evidence that we can collect. Preserve for possible testing and evaluation or trial presentation. Again, we have to keep some of them, take some of them. Documenting the evidence, conditions, circumstances that could possibly change. So, they don't stay the same. For example, you go into a building and there is significant amount of foundation settlement. We're talking about like 6 inches within like a distance of 50 feet or so. You need to document that right away. How many inches? What are the crack widths in the concrete system, and document it. Why? Because this case is not going to solve within a few months. It's going to take at least a year or two, at least. So I need to come back in 6 months, verify, is this progressing or no? That way I can quantify the damage, not just relying on one-time assessment. So that's where the condition can change. Properly collecting failed components, unimpacted components. We do need to document both. Not only the failed one. Why? Because the unimpacted components gives us some kind of idea what were the original condition of the failed component, the impact component. So you go into a structure, we just don't want to document the condition of the damaged area. We want to document the condition undamaged area. So we have a reference. Piece mark classification system. Usually when there's a legal dispute, every component we collect, we have to piece mark it. That's a legal terminology. the mark that you use for each item, physical evidence. That is a unique number, and in all documentations, your R reports, everything, we just refer to those piece marks to just make sure there's no confusion. Another item that you might be interested is called bait number, that probably a lot of you know already. Bait number is, again, a unique number for documents. Piece mark classification is for evidence, for physical evidence, but bait number for documents. Every single page of every document, whether it's a deposition, whether it's a calculation, structural engineering calculation, the plan, there's a bait number assigned to that, which is very unique. So when we're talking about something in a deposition or a court, a trial, or in a report, we can refer to that bait number, and it's very unique. Nobody gets confused. We don't need to say such and such report dated and that by author by that page number that. We just give them the bait number, goes exactly to a page, a specific page number of a specific document. So this is just an example of a legal document in one of these litigation. Okay, remember in the beginning I mentioned to you the slide cover slide was LAX jet bridge failure. This is a component that caused the two victims to be taken to hospital, and I believe they were in hospital a long time. They could not be released. This is that failure. As a 4x4 HSS member, it failed. This picture is I took this picture in a laboratory, surgical laboratory, and they had to cut it in order to conduct the investigation. So if you see this middle piece, it was cut, but it failed. It failed at one section. We'll go through that in a few moments, but that just, again, as a collecting, I didn't collect this. The metallurgical engineer that was involved before us, he went in and collected, and they preserved it in his laboratory, and I went and I inspected it myself. Okay, this is that same picture. The area is underneath here. We're just going to touch on this very quickly because we're in the area that they're talking about in this webinar about the documentation of the evidence. But then in a few slides down below, I'll explain to you what that case entailed and so forth, so you have some kind of idea. Documentation, photography, videography, interview with eyewitnesses, and coordination with other forensic professionals. Usually you don't only have one forensic professional. You have geotechnical, you can have metallurgical, you can have fire expert, and so forth. Okay, chain of custody. What is chain of custody? In structural engineering, you go to a property, you go to a site, and you see some physical evidences. Somebody has to be in charge of that until the case is settled. Then you can throw it out. But until then, somebody has to make sure and is going to be legally responsible to preserve that same condition as the time of the collection for the whole investigation process and for trial or arbitration or whatever it is. So that process of maintaining and holding this in your putting it in your position is called chain of custody. Okay. There is a guideline, a specific guideline by ANSI, ASTM, that is published and explains that procedure. It's for scientists and engineers. It's not for lawyers or other areas of law. It's for us. So it specifically explains when you go into that publication, you obtain it and explains to how to go step by step. It's not a one-page document. It's like a book, and you can go through that process and see exactly how that process works. Okay, Now let's go back to that failure, that LAX jet bridge failure. Again, it's 12:10 right now, so I have 50 minutes for another 40 slides. So I'm just going to make sure that there's a meaningful way of using our time, not too fast, not too slow. So what is this member? This member is an HSS member that was holding up that cantilever portion of that jet bridge that went into and connected to the aircraft, a Boeing aircraft, 737 Boeing aircraft. So it failed like this. This is a few minutes or a few hours after the failure, after it came down. It's right at the site. Somebody took this picture, but there's the victims, or one of the victims was the pilot. He was standing on that piece to let everybody get out, and he was chit-chatting with the last passenger, both of them, and like within 5 minutes, this happened. So somebody took this picture, and it's such a great evidence. And I explained to you why it's such a great evidence in a few moments. This is how exactly it failed. It's still hanging and dangling here, as you can see. But look at the corrosion here. See the corrosion here? And this is a 1/4 inch thick. So look, the corrosion all the way through. And this is the seam. This is the HSS seam, hollow steel structural section seam here. Okay, let's see what's going on. It's a 4x4 by 1/4 inch thick. And I very briefly touch on this, but it's a very interesting case because it involves fatigue and it involves cyclic loading. And what you might say, hey, what cyclic loading has to do with the jet bridge, I explain to you in a few moments. So here, conducting the investigation, identification of debris, destructive testing, as-built drawing, original calculation, shop drawings, inspection records, correspondence. Be very careful with one item. Most people, whether are layperson, engineers, or attorneys, have no clue what destructive testing is. They have no clue. The rest of them, we know that identification of debris, collection, the piece mark and everything, as with drawing, original calculation, shop drawing, inspection record, correspondence. But this is tricky. We need to be very careful with that. A lot of engineers go to a property and they see that the opposing engineer removed some wall finishes or ceiling finishes. They just panic. They say, oh, you did destructive testing without my permission. That's not destructive testing. Exposing structural members is just exposing structural members, removing finishes. Destructive testing has a specific definition. It means you collect a sample from a site, whether it's a steel, wood, or concrete, or whatever. You take it to a laboratory, you test it to the point of failure. Failure, it has to fail. So it involves a laboratory testing. Putting up and examining the condition of a structural member, whether it's has cracks, has corrosion on the steel or whatever, that doesn't constitute destructive testing. A lot of lawyers are very, very confused about that. Okay, what is this? This is an interview that History Channel did with me. It's on YouTube. If you go to YouTube and you type this in, it has 4.5 million views in 1 year. It's a 40 minutes documentary. The last 10 minutes of this documentary, I had the honor, a privilege of being the interview. And very briefly, you can find it in YouTube. For many years, for probably 7-8 years, it was on Amazon, and you had to pay to watch this. But since last year, they've just put it on YouTube for free. So you can go in, and if you are interested, the last 10 minutes, essentially, if I want to explain to you very brief, is that Pumapunku is an ancient site in Bolivia, Southern America, South America. And the History Channel was trying to find out what destructed this structure. These pieces that you see, some of them are 20 tons. And the reason they're very interesting is that this site that you see is way up on the elevations. This is not on there. This is a very high elevation, several thousand feet above the sea. And what is amazing, how these heavy stones were transported there, and number two, how they were cut in such a precise, so precisely. And the question was from me, what caused the destruction of these? You know, this was a structure before, and now it's not. Maybe 10,000 years ago, maybe 5,000 years ago. I'm not 100% sure. It's not documented exactly when they were built, but they went throughout the different part of the world. The interviewer interviewed researchers, scientists, and I had the honor to be the last one because they came and asked me some tough questions. And they told me, do you think it was earthquake? I said, no, based on my research, the nearest earthquake fault was 100 miles away. Was fire. I said, I spent about 2 weeks in, researching this. I said, no. They said, okay, alien. Did the alien came there and caused explosion? No. The only reason that this happened was flooding. The only thing that could possibly happen was flooding. And the interviewer was shocked. He said, flooding? This is way up in the mountain. How do you get it? I said, that's the only way. So, and if you watch the video, I'll explain to you. So, but anyways, after they finished my interview, they went to Bolivia. They found fish fossils everywhere, and they concluded at some point of time the water level was that high or something that created a flooding situation. Anyways, if you like to go, it's on YouTube. The video we can watch it here, but when I have a full day. When I have a full day webinar, I play that.
To get
Here,
a
I just play,
picture of just the modern days,
I
we
just play
do
a few
these
seconds.
type of structures. The model of Pumapunku.
So in I do believe in extra what's that terminology? The life other than Earth, but I do not believe in the like Area 51. Aliens and that kind of stuff. No, but I do believe there must be some kind of civilization somewhere in this universe. Whether they have reached our Earth or not, that's very remote, I don't think. Anyway, so the item number 9, field protocols and tests, depending on the type of material, these can change. This picture is a seismometer that you install when you have suspicion that construction nearby, heavy construction, might impact your client's structure, especially when they're a little bit old. This seismometer, you install it, you leave it there for 2-3 weeks, and it keeps track of all vibrations. And at the end of that 2-3 weeks, you take it out, you look at the graphs, and you determine whether it met the threshold or not to adversely impact your client's structure. So field investigation methods, field instrumentation, destructive testing that we just discussed a few months ago, non-destructive testing. Oh, okay. So when we expose a structural framing member, whether we want to visually inspect it or do some measuring, Schmidt hammer, whatever we want to do, that's part of non-destructive testing. So removal wall and ceiling finishes and exposure of the structural framing, that's what we just talked as different categories. Okay. Development of the preliminary results and findings, review of the documentation, retrieve and review investigation data, review test results, compile and analyze the collected data, self-explanatory. Another example, very simple, we need to go through so I can provide you with information with the rest of the content. This is another example of one of my investigation. As you can see, there are 5 homes on the on the right left. They are probably about 10 feet higher than this parking area. They're 10 feet higher because this red line represents the retaining wall. So everything to the right is 10 feet below that the backyard of these homes. This is a different one than that Las Vegas that I told you, totally different. So what was the problem? The problem was these homeowners were noticing this wall is failing. And they complained to this owner of this shopping plaza on the right hand side. They said, no, it's your own problem because you have trees here in this area, and your trees are pushing our wall, our retaining wall. This retaining wall was built by the shopping plaza, but it was supporting the structures of these homeowners. And anyways, you might say, okay, you have circled these trees here, but what are these trees? These trees are on the lower end. This tree that is circled here, and the shopping plaza owner claimed that they're pushing the wall are here. So all these trees are on the lower 10 feet below on the parking level. So anyways, at this location 1, 2, 3, 4, 5, I examined the building, and I first of all, my understanding was, okay, my client has trees here. Okay, but why do I have problem everywhere, even here, that I have no tree on this backyard? So I show you in the pictures. So as you can see, 7 inches of the deformation at the top. The wall is 7 inches moving away from the building. So obviously, there's a problem. Then we did put that with the condition that it was, and we came up with this schematic. The total height was about 15 feet. This is, you can see the see-through crack. The crack, you can see the other side. This crack was not in any shape or form at location 1. It was like location 3. And there's no tree on any of these other homes except this home, first home. So we noticed that and say, hey. Anyways, another case of determining causation and responsibility, why it happened and what the causation. Very simple on the right-hand side, a bulge in the stucco up to about 4 inches. Stucco of a multifamily building bulge. That's another category we can discuss. And it's a little tricky why it happened and what did cause it. Okay. Determination of causation and responsibility. Number 10, identify all possible scenarios, eliminate unlikely scenarios, to converge what are the most likely causes of failure and key technical causes of the failure that can be supported by facts, understand the process of design, construction, inspection, and maintenance prior to failure. Now, over the next few slides, we explain what happened in this case, which in my opinion, one of the very interesting cases that I've done. This is the area that the failure happened. This is the cantilever section of the jet bridge. This area, I took a picture from below. These pictures are by me. I took a picture by myself. Okay. This member, this is a new, it was removed and replaced. The old jet bridges had all 4x4 by ½ inch by quarter inch HSS section. After we determined that they were defective, the design was defective, they changed them to a larger section. I wasn't involved in the design, but I know that they changed. So this is not a 4x4 anymore. It's like a 6x4 or something like that. Anyways, so this new one that I had a chance to inspect, that it was a year after, this is the section of that old 4x4 that failed. So as you can see from this location, it cantilevers, it gets supported here on the left-hand side and gets supported here, and then it cantilevers this much. And okay, this is from another angle. from another angle. And let me explain to you. Okay, this is that piece that I took picture myself again. This is the failed member. One end, the middle section that was supported, and then the rest was cantilever. So when you go back to this picture, this is the one end of the support, other support, and then the cantilever section. So go back to the failed member. This is the closest part to the aircraft, and this is the most distant part from the aircraft. So this area failed. This area failed, and there's a plastic. You can see that it says the samples, piece numbers, everything, piece mark numbers, everything. Okay, now what happened? Again, the same picture we looked at a few minutes ago, and a closer picture, and they had to cut this. This is a cut, but this is not the cut. This is the actual failure, and you see all corrosion marks on it. So let me quickly explain to you. In order to explain to you, let me go back to this picture. Okay, this picture, aircraft, jet bridge, cantilever section. So there's a phenomena in a structural structural design. It's called fatigue and cyclic loading. Let's just very briefly touch on that within a few minutes so you can have some kind of idea. Mostly mechanical engineers are very familiar with that because it's on automotive and in their field, they deal with it on a regular basis. Structures, they don't deal with that. Maybe 1% of us deal with that. But here, what happened? Why cyclic loading here? Okay, Boeing 27, we went through the LAX record. We found that this particular Boeing that we knew their record number, all the serial number, everything, was serving like 12 years. I'm sorry, I take that. Oh, I was correct. Yeah, we checked the Boeing that was coming at this particular gate, particular section, particular airline, that particular airline that involved in this incident. We checked it like last 12 years, it was coming there. We went through the record, how many flights a week, how many times, how many passengers, and with this particular jet bridge involved in this particular jet bridge. Okay. Every time a passenger weighing anywhere from, God knows, 80 pounds all the way to 300 pounds, steps from the aircraft door into this cantilever portion of jet bridge, what happened? Essentially, before they step in, there's no load on that cantilever member. As soon as they step on it, whether it's 80 pounds or 300 pounds, they're putting a load, they're putting a stress on that cantilever member, the 4x4, right? As soon as they walk into this area to the right-hand side, then that load is eliminated. So for a few moments, there's a load on this HSS member, then there's no load on. So the member goes to a stress level, then the stress level is released. Imagine that 200 or 300 passengers, few times a day, 12 years, how many cycles that HSS component is going through? It can be millions. Now, why that number of cycles matters? Because when you go to fatigue design, number of cycles directly impact your capacity. The more cycles you have, the more reduction we have to do in our allowable stress. In a simple language, a little bit more complicated. We use SolidWorks software, $10,000 software, in order to do very detailed final element analysis of what happened over the course of 12 years, 365 days a week, service, 200 to 300 passengers, weights. We did that modeling, but simple language, if you go to either older version of allowable field construction manual or the newer version, simple language is that you need to calculate the cycle when you design. then there are some documentation and literature, you go based on the cycles, you reduce your allowable stress. Sometimes it's very significant. You can only use like 15% of your allowable stress. Like imagine from 36 KSI or whatever KSI that you have to use based on the, whether it's LRFP or it's allowable stress. Instead of like 30 KSI, you're forced to use like 3,000 PSI. And if you do that, your member sizes are bigger and all of a sudden instead of being too small, because cyclic loading, what happened is it starts propagating cracks, micro cracks in the member. When you have permanent solid static loading, that doesn't happen. Cyclic loading causes micro cracks. And micro cracks by themselves cannot be very dangerous, but as soon as you get close to the ocean and aggressive environment, the chlorine gets into those micro cracks and they cause further cracks and they corrode that area, and this is what happens. So fatigue itself is a problem, but when combined with harsh environment, it can be disastrous. So imagine this is what happened. And now when we look at this picture and this picture, you see the corrosion here. Now this picture more clearly shows the corrosion, and of course the very first picture at the site. And then this picture, this is by the metallurgy engineer, and this is the seam of the HSS, and it identified the design flaw. So I reviewed the design calculation, structural calculation, and there was no reference to fatigue, nothing, or cyclic loading, nothing. Just a simple modular section. This is my demand, this is my section, boom, 4x4 steel section, check mark. That was 1 page, or I don't know, 2-page calculation. And it was not within the United States. It was in a foreign country. That designer had no clue about what disaster this can be, and God knows how many of these jet bridges are built and used throughout the world. Anyways, done with that jet bridge. We're at slide 54. We have about 25 minutes. Learning from this. This is the 11th number of them, 11. So we're going to go through some of the cases. Understanding the mechanism, failure mechanism, in order to avoid them. And obviously, every building cycle, every three years, the building code change, because we're trying to reflecting those into our new building codes. Imagine back in 1920s when our building codes were, like, I don't know, 10 pages and so forth, and then gradually build up. And now it's like a full library that you can't keep track of it, and you have to have PDF version and everything. So God knows, 50,000 pages or so combined with the standards. So ensuring our structures are safe and improving public safety. Question from Roberto Sanchez and Doug. If I may, I'm just going to quickly touch on these two questions. Do you test the air at the truck or the chute when pumped? Air. Oh, the air that they add into the concrete in order to make it more workable. I don't know. I know, all I know is that they collect a sample and they send it to the laboratory for test, and that's what I understand. And then the other question is very interesting. Who did the design? Again, it was a foreign country, and apparently he or she was a structural engineer. It was not an other engineer. It was a structural engineer. Maybe it was a civil engineer practicing a structural engineer, but I almost 99% sure it was not a mechanical engineer. The mechanical engineers know much better than us about that issue. So some historic failures. Let's take a look. 27 AD amphitheater collapse, Tacoma Bridge collapse, 1940. This is one of the very interesting one. Happened, God forbid, 80 years ago or so. And then there were 1980 platform collapse, Alexander Kielland collapse in Norway, Hyatt Regency, Northridge earthquake that caused a lot of failure, and Genoa, Italy bridge collapse. We just touch on these briefly, very briefly on each of these. And okay, we look at the question 5 minutes before we end. Okay, Tacoma Suspension Bridge opened July 1940, collapsed 4 months later in 1940, November. This picture is during the oscillation when the wind apparently lasted about 3 hours or so. And look at this side. Look at this side. Do you see this side? This is a girder. And the girder is not short. It's not like 12 inches. It's several feet tall. I think it's about 3 feet tall. And remember that in a few moments, I'll explain to you what happened. What was the mechanism? I'm sure this is a historical. A lot of you already know that. But, the specific causes still debated, but 3 theories. The top theory is aerodynamic instability. The next one, random turbulence, and then periodic vortex shedding. Let's go through one and see what happened. So the motion was about 3 hours. The wind was only 42 miles per hour. The frequency of the bridge torsional oscillation was observed at about 12 cycles per minute. A support cable at midspan snapped, resulting in unbalanced loading condition. Among other things, wind drove the bridge to oscillate at its natural frequency. Frequencies of wind and bridge were then in resonance, causing amplification. You and I know about that in structural, in earthquake engineering, when the frequency of the building and the frequency of the waves match, it amplifies, significantly amplifies the shaking oscillation, and we call them resonance. Same thing here. Excessive flexibility of the bridge, not being sufficiently stiff, and lack of sufficient stiffness here, which is both of them. Okay. This is the as-built plan for the bridge. Obviously, it was a noble design. But because based on my research, because the government was struggling to provide the budget for this, the structural engineer had to go through, whoever did the design, had to go through several innovation and make it more cost effective. And eventually, as you can see in this red dashed circles, these are the 2 girders on the side, which I showed you in the beginning. I said they're not too short, they're about 3 feet tall or so. So these are those girders that the deck is essentially supported and then hung from these cables. Okay, these are tall. I think it's about 3 feet or so. Why their height is so significant, I'll explain to you in a few moments. Okay, usual bridge design back then were done by these like a truss section. As you can see, this is a member, diagonal member, but then air can go through, the wind can go through. The Tacoma Bridge, this section is solid. So obviously it resists that air, and then that resistance had to get transferred somewhere through the load path, get transferred to the deck, and then cause all that kind of problem. So that's one of the primary reasons. So that was the Tacoma Bridge. Another disaster that happened. This disaster goes back to fatigue. This one, that was resonance. Again, subtle issue. They're not very They're not very crucial issues, they're subtle issues, but essentially Alexandra Kiln platform built in 1976, 4 years later, collapsed, 120, hold on one second, I need to get rid of something quick. This is one of my son's laptop that I used today. Anyways, so in 4 years, it collapsed, 123 lives perished. Cause of the accident was initial weld defect, small, very tiny defect in this humongous structure that accelerated with fatigue failure. Remember, the most vulnerable part of a structure for fatigue and cyclic loading is not the members, not even the bolts, the valves. Valves are the most vulnerable component and part of a structure for fatigue. Okay, so the same problem here, more or less, if you remember that LAX jet bridge, you may say, oh, there was no weld there. Yeah, there was a weld, the seam. Remember the HSS has a seam, the jet weld, there was a weld there. Here, fatigue crack propagated from a welded joint. Let's go and see what happened. This is that structure, this one on the right-hand side. See this humongous column? These columns are, several meter diameter in Europe, and then there are braces. And this is one. When you go under this water, this is what you see under the water. The platform is on the top. This is they were floating. And there was a hydrophone installed here. Hydrophone is to determine the sounds under the ocean, under the water. So fatigue crack occurred from a pre-existing crack in a weld, fillet weld, between the hydrophone support and the brace D6 here. So that's the area. So very minor initial defect, but it took 4 years. Why fatigue? Because fatigue only comes from cyclic loading. It doesn't come from static loading. Why cyclic loading here again? Similar to the jet bridge, waves. This was a floating structure. So it goes up and down, and that gives you reversal of loading and cyclic loading and fatigue. Unfortunately, this is the picture. This is Norway celebrates this or respect this event every year on the day that it happened. They remember this. This is in the museum. It's kept there, and it's, as I said, several meters diameter. That very failed member. They just kept it there, and this shows the process that happened. And this is that location. This is a video. Again, we don't have time to watch the whole thing. I'll just show you a few moments of that.
Sammen med verdifullt utstyr,
Like
4 flunkende 18. november 1983,
They took
og den la
this
seg
video.
over og
They took this video and it's okay. Next failure, historical failure, Morandi Bridge in Italy. Very large, longest span bridge. The collapsed section is here, and 43 lives, 2018, a tragedy. The collapsed section is here. As you can see, it was over 1 kilometer long, which is about 0.8 miles or so approximately. This failed section is enlarged here, and 200 meter approximately, that's approximately about 700 feet long, approximately. And the cables. What's the problem here? Corrosive environment, right on the, as you can see, right on the water area, and corrosive environment. These cables inside, they were encased in concrete, and they corroded. When you encase cables in concrete, essentially you're not protecting them. There's no way for us to stop moisture from getting inside the concrete into the cables, there's no way. What it does, if they didn't encase them was much better because the moisture did not get trapped. Now it got trapped, it corroded and failed. And the bridge collapsed. This is the scale, person here. So it's quite tall. It's about 300 feet above the water level or above the bottom. Okay. So, almost getting close, 15 minutes left. I think I went too fast, but that's okay. We have more time for discussion. Having consistent assumptions with the structural behavior, software. Software are great. Back in late 80s, when the computers started to develop personal computers, we used to call them personal computers back in 80s. And I graduated in 1984, 85. So computer was so amazing. And I like 80 or so when I was first computer we had in our office. I was so excited, a young engineer, and everybody told me, hey, you want to become successful, you need to learn personal computer. Before, it used to be IBM, it's a whole big room with, the Fortran punching cards and everything. But now personal computer was a technological masterpiece. So I learned I got a few computer programs that were made back then, and I modeled them, structure, designed them. But very soon I learned that I was maybe about 28 years or so. I discovered that, hey, I know why I discovered that, because I worked for my old boss. My old boss, back then he was a 60 years old or 70 years old, brilliant, a structural engineer, brilliant. And he was in deep trouble. Why? Because one of the buildings that he designed, during the construction, wind came in and one of the masonry walls that didn't have proper temporary support failed, and then he was in trouble. It was not his fault, but he was pulled into this dispute, and he asked for my help. So I got in, I jumped in, helped and everything. And I found out that the engineer before me who had designed this thing, he used software, and the software that he used, I went in this, and again, I was a young engineer. I didn't have any idea about what's going on with the software and things back then. And I found somehow I got a hold of the software program company, and they said, hey, did you not see the disclaimer? I said, what disclaimer? I said, you are ultimately responsible for the design. We're just helping you. You're stamping, you're signing. So at that point, I said, oh my God. So from the very beginning of my career, I learned that, they don't help you when something happens. So you need to be careful. So the engineer before me, he was a very good engineer. He designed this. He had some flaws, but it was a good design. But again, that flaw contributed to, the entity was investigating this failure. They found out that the design had some defect that contributed to that failure. Anyways, from day one, I learned that beginning early, I learned that, hey, you need to be careful. So every time I design since then, I always go check by hand again and again, even though it takes me a lot of time, but it's better than doing by hand, fully by hand. I do a design by software always, but I check it by hand. So instead of back then, when my old boss was working, he said, Casey, back then we used to use everything was hand calculated, not even the calculator, with, what's it called? The ruler, special ruler. They used to use, those rulers in order to do logarithms and calculations. So back then, if a job took 200 hours, now the same job takes maybe, I don't know, 50 hours. And, but now I learned to maybe put another 10 hours to just do back checking. Peer review, coordination, communication among design professional and among contractors and design professional and instrumentation. And that's it. That's the end. This is one of my brilliant assistants, and this is my son. He is also, he graduated from UCSD in instructional engineering last year. So these gentlemen, young gentlemen, helped me with this to put together this presentation for you. And now we have about 8 minutes. Let's open this up. So we answered the first question. The second question, for the jet bridge failure, it looked as though there were weld in the vicinity. Did residual stress enter into this analysis of failure? Okay, Jeff Thomas. I don't know Jeff Thomas' background. Are you a structural engineer? Are you? I don't know, but the residual stress enter to the analysis. Are you? You need to give elaborate on that. But obviously, I explained to the audience earlier that yes, it does. Well, is the most vulnerable component in a fatigue and cyclic loading situation. I've noticed that when it becomes to understanding of concrete failure, most structural engineers reference building code ACI, PCA, etc. But a few refer to guideline of International Concrete Repair Institute, ICRI. Have you explained the project with concrete failures in which repairs of concrete were not performed by standard? And did you use ISI guideline to evaluate the way the repair were performed? Okay, this is from an anonymous attendee. Okay, sir, so in order to answer your question, ACI and PCA, yes, there are reference standards. The reference standards, they're referenced in the model building codes or state building codes. So these are the standards, and building codes refers to them. And the ICRI is another reference, the guideline that I've noticed that, I've seen that. And whether I personally use that or not, sometimes, yes. But again, the repair process is something that is done after the diagnostic process. So the diagnostic process is something that I get really involved, but the process of what is the most viable, what's the most economical and preferred method of the repair or removal and replacement, that is something after my involvement. So I'm sure that those design engineers, architect, contractors, they take this very useful guideline and use it. Okay, Roberto Sanchez. I have noticed that when it comes to understanding concrete failure, most structural engineers. Oh, okay. It was Roberto Sanchez. Thank you so much, Roberto, for your beautiful question. Jeff Thomas, not referring to HSS symbol. Oh, yes. I did refer later because again, I can't state everything in the very first second. I have to, I have to go step by step. But thank you very much, Jeff, for reminding me that, because yeah, that is very crucial. Licensed structural engineer. Oh, Jeff is a licensed structural engineer. Beautiful. Thank you, Jeff. Again, it's my privilege to be here. Oh, okay. The residual. Okay, the residual stress because of the seam. As I said, we when we were analyzing and determining the causation, we did two ways. We did it with the hand calculation based on ASC, ASC, the American Institute of Construction, Institute of Concrete, Steel Construction manual, whether the back then, whatever was the manual back at the time of the design or the new one, they use those for hand calculation. Then we use the SolidWorks and the modules, a specific module for cyclic loading and fatigue. They have a special module. You have to purchase that on the top. So I did manually check. Then we did go through the steel, the SolidWorks, and we did take into account various kind of features, and I believe residual stress was one of them. Yes. Okay, then that's Jeff, and then so there's another one. There's slide rule. Yeah, slide rule. Thank you, John. How do you know that? You must be my age. I mean, I never used the slide rule because I was born in 1960, but I know like 7-8 years before me, they were used to use that. 7-8 years before I started practicing. So like I started practicing like 1985 or so, but I know like 1970, they were still using a slide rules, but after like 1975, I think small hand calculator came in, and so anyway, thank you so much for reminding. I tell my son, who is now a fresh, engineer, gonna say, hey, you need to use the slide rule. What is a slide rule? You're too young to know. It looks like okay, here. Do you see me? I see, of course I see. The FIU pedestrian bridge collapse during construction might be reviewed as an example of construction. Thank you, sir. Thank you so much, Roberto. I'm so impressed with the knowledge, extent of knowledge of some of our participants. Thank you, sir. By the way, apparently a new failure happened a few days ago in East Coast. A bridge collapsed. Apparently a truck caught fire under the bridge, and the bridge, because of the excessive heat and damage to the structural sections, it collapsed. It looks like the crack started in HAZ, which was this taken into account? HAZ, Matthew, HAZ, I'm not sure what you refer to. If you could type that in, it would be more helpful. Thank you. What is the ultimate cause of retaining wall deflection between the shopping mall? Ultimate cause? Beautiful question. Usually is design defect, but I didn't get into that case. It didn't get him. It didn't go to extensive forensic investigation. They settled it. As soon as I gave them a very preliminary report, they settled it. Alberto and Jeff Lewis. Oh boy. What is CMU? CMU is concrete. It stands for concrete masonry unit. So it's basically masonry blocks, CMU. And there are CMUs, remember? And there are another masonry type, which is called URM. And URM, it stands for unreinforced masonry. URM, unreinforced masonry, which when there's no rebar in them, which back in the old day, like 1920, and they used to do that, it becomes URM, and it's very dangerous. Okay, 2 new messages. Berto, excellent presentation, Mr. Hemati. I greatly enjoy learning from you. wonderful experiences. Thank you so much. I'm honored, Roberto. Thank you. Neil Hansen, at the University of Utah, sliders were still required for exam 1973. Oh boy, beautiful. A scientific calculator cost over $300. Yes, I remember. By 1978, inexpensive calculators were the rule. Yeah, you're right. I love those. I love the time when we have to do everything by hand. Because we were putting four times more time, and we were getting paid much more. My old boss said, the gentleman that I told you is brilliant engineer, he said, Casey, my salary back in 60s was higher than a brake surgeon. And I believed him because he had a very good life. He lived in a very good neighborhood, very good man. God bless his soul. So, have you looked at the problem with the Millennium Tower building in San Francisco? Have I looked at it? I know it's a geotechnical issue, but that's a very, very, very expensive issue, a problem. I haven't looked into it, but I know about it a little bit. Would you call this as a design error or a foreseen load condition? Oh, that one, James? James McKay. I don't know. I'm not sure. I can't comment on something that I don't have any involvement and I have very, very limited knowledge. I don't know. I'm sorry, James. And looks like I answered everything. Let's see. Truck fire in Philadelphia. A professor at Dexter suggested that paint be used in the future for bridges. Your thought? Well, the paint, yeah, maybe this type of paint, maybe it can help, obviously. And there are a number of ways that you can fireproof these kind of vulnerable exposures. I'm sure that would be one of the applicable ways, obviously. Thank you so much, Jeff, for your beautiful comment. HAZ is heat affected zone. Oh, my ignorance. Thank you so much, Matthew. Yeah, and we go back to the question for heat. Question for HAZ. Oh, it looks like the crack has started in the heat effect. And what is? Oh, okay. Thank you. Great observation, Matthew. Affected. I have to be honest. I'm not too sure, but again, it propagated, and we established the design flaw, and then that was much easier to go for our client and for the victim to collect the compensation than going to the going after the manufacturer of HSS, and you don't. But I believe, yes, it was part of the it was one of the issues because again, as I said, the weld is the most vulnerable section. I wish I had this course at college. Stephen Ferris. Oh, sir, I would have been so invaluable in my early years. Thank you for sharing your knowledge with us. Steve Ferris, class of 90. Oh, beautiful. Thank you, sir. I'm really honored for all of these beautiful compliments. I'm really honored and flattered. Thank you so much. And let me make sure that I took care of all of these. Thank you, gentlemen. Thank you so much. And I think, Ashur, do you think you're done with the presentation? It's past minute 5. Oh, we have another comment. Neil Hansen. Let's see what Neil says. Looking at the jet bay square tube, it looks like the failure cracking started along the toe of the fillet weld, connecting the block to the top of the beam, then propagated towards until the top flange failed in tension. Looks like it took some time, judging from the corrosion in the crack. Is that correct? Oh yeah, it took several, of course, it took several years. You're absolutely correct. Neil, yeah, and thank you for your beautiful observation. Thank you, sir. Okay, ladies and gentlemen, I truly enjoyed today's um, interaction with you, and I look forward to future webinars that I can be enjoying this kind of uh, communication again. Thank you, ladies and gentlemen. Have a beautiful rest of the day. Bye-bye. Thank you, everybody.